Hello, everybody. So today we're going to look at section 5.3 for the third time, I think. So what we're going to do is we're going to finish up our talk about trees and we're going to do some proofs. So yeah, so let's get to it. So I think for the proof that we're going to do, let me just double check this. Full binary tree, full binary tree. So we're going to be talking about full binary trees. So let's just get the definition from the previous lecture. I'm going to have to just write it again. The definition of a full binary tree was this. So, full binary tree. Now, this was one of three different tree varieties that we looked at in the previous lecture. So there was like full binary trees, and then there were just extended binary trees, and then there was just rooted trees. Rooted trees are just basically trees. So, all right. So, basis step. What is that? So this is review, so we're not going to talk about it too much right yet. But the basis step was a single vertex is a full binary tree. Single vertex R is a full binary tree. All right. So what is the recursive step? So the recursive step, you have a left and a right subtree, remember? So if T1 and T2 are disjoint full binary trees, with roots R1 and R2. I don't know if I bothered to say that last time. Yeah, I don't think I need to actually, so let's not. So full binary trees. There is another full binary tree, comma. There is a new binary tree, new full binary tree called T1.T2, consisting of a root, vertex R, and edges connecting R to the root of the left subtree and the right subtree. And, the left subtree is T1 and the right subtree is T2. So to the root of left subtree T1 and right subtree T2. All right, so that was our definition here of a full binary tree. And just remember how it works, right? Like if you've got, this is just an example of a full binary tree. Actually, let me just use colors here. No, I can do that. So like this could be your T1, this could be your T2, and then in order to form a new binary tree, you just add a new root that you're going to call R, and then you have to connect that root R to the previous roots of the left subtree and to the right subtree, and that's how you get a new binary tree. So there you go. So that's a full binary tree. And the reason we say it's full, if you remember, it's because from every vertex it branches out either into two things, or if it's what we call a leaf, then it doesn't branch out at all. But what it never does is just have one side but not the other. So it can never go left but not right. Right? So it's either two or nothing coming from a single vertex. Talking about down, right? Because there's one edge up, but from this vertex, there's not two branches down. So it's either 2 or 0. And that's a full binary tree. All right, so what are we going to do with it? Well, we had these definitions last time, but we didn't do any proofs or anything based on them. And so we're just going to go over the ones in the book here. So let's see here. So here is how we're going to talk about the height of a full binary tree. So definition. The height, we're going to call it h of t of a full binary tree is given by the following. So full binary tree is given by. All right, so this is going to be a recursive definition. So base case or basis is going to be, so if we have just a single root, we're going to say that the height is 0. So the height of the full binary tree that is just R is a single vertex R is h of t equals 0. So we're going to call that a height of 0, right? So we can draw some pictures over here. A line over here. So like if you have this, we're going to say h of t 0, right? And probably you can imagine what's going to happen if you have this kind of thing. You're going to want that to be 1, right? And that, and so on. So if you had something like this, and I could have drawn this side in, but I don't want to. It doesn't make a difference here. So this one is at one of the trees that has height, 2. All right. But that's not the definition, right? The definition is the definition. So we know that a single vertex is height 0. And then what the definition is going to say, so this recursive step is going to say, recursive, what's it going to say? So T1 and T2 are binary trees where we know the height. So if T1 and T2 are full binary trees, then the full binary tree, we know how to combine them. You write it T1 dot T2. And how are you going to calculate it? So it's going to be is given by this formula. So h of t is going to be, what you have to do is you have to take the maximum height of the T1 and the T2. And then you're going to have to add 1. And that's the formula. All right. So that's the definition. So just to think about this for a second, right? So based on our intuitive definition, if this was T1 and then I gave you a T2 that looked like this, so this is T2, then what would the height be of these two, right? So this one right here would have a height of 1, right? And this one over here, you can probably guess, would have a height of 2, right? And so if you wanted to combine those into one tree, And so you put a new vertex up there and say, well, what's the height of that whole thing now? Well, you basically just added 1 to the height of the whole thing, right? So this is 1, and then you're going to add that to whichever one out of this one and this one are the larger. So the total height is 3 here because we've added 1 to this number right here. Okay, and so that's how the height works for a full binary tree. So let's see here. So that's just a definition. So there's not like a proof to be done there. Let's see here. Okay. So another definition. This is just too many definitions. I didn't realize there were so many that we needed to do. Definition. So what you can do is you can actually count the vertices in a full binary tree a certain way, pretty much the same way as what we did for the height. So so the number of vertices in a full binary tree is given by vertices of a full binary tree. What is it? It's going to be n of t. That's going to be the number of vertices. And it is given by, and like before, we got a basis step. So if you've got, your basis is going to be a single vertex, right? So if you have a single vertex, then, how many vertices are there? There's 1, right? So number of vertices for the basis step is going to be 1. So if T is a single vertex, then N of T equals 1. All right. Now for your recursive step, it's going to be almost exactly like the definition for height, right? Because, think of it this way, right? So suppose you had this. You had 3 vertices here, and then you've got another one over here, another full binary tree, right? And you got some. And so there's 3 vertices there, and there's 1, 2, 3, 4, 5 here. And then if you add a new vertex in, how are you going to get the number of vertices in this resulting tree? Well, you're just going to have to add up the 3 and the 5 and the 1, right? So that's all, right? So it's just add those all up, and that'll be the the number of vertices in this binary tree. So let's see. If T1 and T2 are full binary trees, so T1 and T2 are full binary trees, then the number of vertices of T, with the number of vertices of T equals T1 dot T2 is N of T equals, well, count up the vertices in T1, add it to the number of vertices in T2, and then add 1 for that new root. And that's the definition. Okay, so that's still not that's not a proof. We don't need to prove this. This is the definition of number of vertices, right? So number of vertices N of T, and then this definition up here was IH of T. Okay. Oh, I wanted definition. Okay, so now let's do a proof. I think we're going to do a proof. Okay, so theorem, yeah, theorem. So theorem means we're going to do a proof. So theorem 2 in this book, this section. What's it says? What's it says? Englishing hard. If T is a full binary tree, then the number of vertices of that full binary tree is less than or equal to 2 to the height of T plus 1 minus 1. Okay, so this is a theorem now, right? This is making a claim about something the number of vertices has to satisfy. So number of vertices is less than this number. So what is this number counting up? Well, I think probably what's going to happen, and we're not going to actually have to look at this, I don't think, but what's probably going to happen here is if you have like, so this is a full binary tree with height 1. Here's a full binary tree with height 2. Here's one with height 3. Now this is just one of them, right? Now, if you count up all of the number of vertices here, right? So the n of this t is what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? In this case, it was 15. That's how many things there are. And so if you just start removing some of the vertices, then, if you start removing some parts of it, then it will be smaller, obviously. So I think the idea is that the one like this that has as many vertices as possible is actually going to match this formula. And if you were to, for example, erase this and erase this, you've now got what, 2 fewer vertices, right? So it is what it is. So this is going to be keeping track of what is the maximum number of vertices a tree could have given its height. So in this case, I drew one with height 3. All right, so so let's go ahead and try to prove this. So we're going to prove this with structural induction, okay? So let's prove it. Proof. So we got to remember how structural induction goes. We didn't do it in the last section, I don't think. Maybe we did. Maybe we did it in the 2 lectures ago. But basis step. So for structural induction, the basis step is going to be showing that the basis tree basically has this property. Okay, so we need to consider a single vertex. So we need to show the basis object, which is a single vertex. Satisfies the theorem. All right, so that's what we're going to do. So what you do is you look at a single vertex. So we just say, well, let's look at a single vertex. Let T be a single vertex R. All right. Now we happen to know both the number of vertices of that and the height. So what is the number of vertices of a single vertex? It's 1, right? And also, what is the height of a single vertex? Well, the height of a single vertex, just go back to your formula, or not formula, but to your definition, right? And it says the height of a full binary tree that is a single vertex R is h of t equals 0. Okay, 0. So then what we want to do is, first of all, not be confused by our n's and h's looking the same. and just verify this formula here, right? So let's just check if this is true. So we have, n of t less than or equal to question mark, 2 to the h of t plus 1 minus 1. Well, let's just put in the numbers and see. So n of t is 1, and that is supposed to be less than or equal to, question mark, because I don't know if it's true, 2 to the 0 plus 1 minus 1. That's 1 less than or equal to, what is it? 2 to the 1, which is 2 minus 1 is 1. All right. Yeah. So that checks out. So it's fine. I don't want to check mark. So it works. Formula is valid. It's okay. All right. Now we need to do the induction step. So for the induction step, what you have to do is you have to assume that everything that you build objects out of has the property that you're looking for. So what you're going to do is in the induction step for full binary trees, right? You have I don't want to do that, but you have a T1. Well, yeah, I guess I do. Right. You have a T1 and you have a T2. And then you make a new one by adding in this new vertex, right? And then connecting those dots. And so what you have to do for the induction step here is you're going to assume that the T1 and the T2 satisfy this underlined property here already. So they satisfy that property. And then we need to show that the new tree, T, satisfies the property. So you assume, for your induction step, assume, that's the wrong color. Right. Assume that T1 and T2 satisfy the property. What's the property? Well, it's the one that we underlined. So the property is that the n of T1 should be less than or equal to, what was it, 2 to the height of T1 plus 1 and then minus 1, I think. And then n of T2 needs to be less than or equal to 2 to the height of T2 plus 1 minus 1, right? And now we need to look at 2, or T, the combination of T1 and T2. So let's look at, consider T, which is going to be T1 dot T2. And we need to look at the number of vertices of that. Okay, so let's do that. So we have n of T1 dot T2 is going to be equal to, all right, how do we do it? So in order to, so notice I put an equals here. Actually, I'm going to, nope, that was not what I wanted. I'm going to move this over to give myself more room to write. I don't know how much space it's going to take. All right. So we want to look at the number of vertices of T1 dot T2. So in order to do that, we're going to have to look at our definition of the number of vertices. So the definition for the number of vertices said that the way you calculate the number of vertices is it's number of vertices of T1 plus number of vertices of T2 plus 1. So you say it is number of vertices of T1 plus number of vertices of T2 plus 1. Okay, that's fine. I'm going to bring this over here. I'm going to recopy it because I didn't give myself enough space. Oops. Duplicate is what I wanted. Duplicate. Okay. So we've got this right here. But then what you want to remember is we've got the formulas we've got the formulas from our what's it called? from our induction hypothesis, right? So what we know is that this one right here satisfies that it is less than this or less than this value, and then you've got this one right here is going to be satisfying this one. So if you put those numbers in, we can say that this is all going to be less than or equal to, and then put in the values. So for T1, you've got 2 to the h of T1 plus 1 minus 1, and then plus, now n of T2 has to be 2 to the h of T2 plus 1 minus 1. And then you've got this plus 1 here on the end. So what is that all going to work out to? It's going to work out to yeah. So what I'm going to do is work out this left side here. So I'm going to put a less than or equal to. So we've got a -1, a -1, and a +1. I'm talking about here -1 and a -1 and a +1. Let's just combine those. So I'll have 2 to the h of T1 plus 1 plus 2 to the h of T2 plus 1. And then overall, the -1, -1, +1 is a -1. Okay, so far so good. Now, here's where you have to get a little bit sneaky. So you've got these two values here, all right? 2 to the h of T1 plus 1 and 2 to the h of T2 plus 1. And we need to kind of combine those into one kind of statement here. So let me just like take a color here or something. So here's the idea. So imagine a couple of powers of 2. So let's say you had 2 to the like 7, and then you had 2 to the 5, right? Now, you can't really like add those together. They're not like terms. But what you could say is that like 2 to the 7 plus 2 to the 5, you would know that it was like less than or equal to like 2 to the 7 plus 2 to the 7, right? Because if you replace one of them, in this case, the 2 to the 5, with the bigger one, 2 to the 7, then you've made it bigger, obviously, right? We replaced 2 to the 5 with 2 to the 7, it got bigger. So, yeah, so you make it bigger. But that's another way of saying, like, you could say that 2 to the 7 plus 2 to the 5 is less than or equal to, if you, that's 2 times 2 to the 7, right? So you could say that it was less than or equal to 2 times the max of 2 to the 7 and 2 to the 5. Okay? And that would be true actually for any two numbers, right? It doesn't even matter like that it's 2 to the 7 and 2 to the 5. You would be able to do the same thing with like a plus b is going to be less than or equal to whichever one is bigger, double it, and that's as big as it possibly could be. Okay? So this is just kind of scribbles over here to justify what I'm about to write, but that's going to be true for any numbers a and b, right? Whichever one's bigger and you double it, that's as big as the thing could possibly be. And that's what we're going to do here where I've got that pink underline. So this is going to be less than or equal to 2 times whatever the maximum of 2 to the h of T1 plus 1, comma 2 to the h of T2 plus 1, whatever that is, and then minus 1. Okay. So does that make sense? Oh, whoa, 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 whoa. That was fine. No, that's fine, actually. Okay. Um, Now then what I want to do is I've got to somehow simplify that that statement there. So here's the thing. We need more of this kind of scribbling. So I'm going to actually erase this real quick. So hopefully you get it from the video since it's not going to be typed up in the notes for you. So we got this, and that is what we used for this. Okay, now what are we going to do about this bit? So for this bit right here, here's what you want to think of. So let's just say that I've got like a 2 to the, let's say 8 again, and then let's say, why again? We didn't have that before. And then like a 2 to the like 13. Okay. And let's say we wanted to know the maximum of this. Well, what you could do is it's like, okay, so it's 2 to the 8, 2 to the 13, and you want the maximum of that. Well, since they both have, right, they both have the 2, that part's the same, you could actually write it this way. You could say that instead of being the maximum of 2 to the 8, 2 to the 13, it's actually 2 to the maximum of 8 and 13. Does that make sense? Because like just verify it, right? Like 2 to the maximum of 8 and 13. What's the maximum of 8 and 13? It's 13, right? So this is 2 to the 13. But here, what's the maximum of 2 to the 8 and 2 to the 13? It's 2 to the 13. So it actually doesn't matter whether you do the maximum here or whether you do the maximum here, because they're both 2 to the something. So that part's the same. So the part that's different is the 8 and the 13. So the only part that's different is the exponent. So you might as well do the maximum as part of the exponent. What's that mean? What that means is down here, I can say that this is less than or equal to 2 times. Instead of putting the maximum right here, I can move the maximum up as the exponent and say that this is 2 times 2 to the maximum of h of t and h of t1 and h of t2. So h of t1, h of t2, I'm going to change something here that you'll have to notice. Plus 1, minus 1. All right. I actually did something sneaky there. So I did what I just said with one sneaky thing. So imagine you had this now, maximum, again, let's say 2 to the 8 plus 1, 2 to the 13 plus 1, like that. Well, if I do what I did on the line right above that, I could say that that's the maximum of, and it would be, well, 2 to the maximum, actually. It'd be 2 to the maximum of, and then you'd say 8 plus 1 or 13 plus 1, right? According to what I wrote on the previous line. But they both have a plus 1. So you can kind of write it like this. Not kind of, you can. You can do the max of the 8 and the 13, and then you could add a 1 on the outside of the maximum, and that's going to give you the same result, right? Like this bit right here is going to give you maximum of 8 and 13 is going to give you 13, and then you add 1 and you get 14. Well, that's just the same as if you took the maximum up here and got 14 from this. So it was sneaky there, and this had a plus 1 and this had a plus 1, but rather than put that in the max, I put the plus 1 outside of the max. Okay, now why did I do that? Well, the reason I did that is because if we look at this right here, actually not the 2, I think we just look at the if we just look at the definition for height, actually. So let me undo that. So if you look at this definition right here, maximum of the height of T1 and the height of T2 plus 1, we've actually seen that before. It's the definition of height, right? Look at this. Maximum h of t1, h of t2 plus 1. So this right here is just the height of t. So we're going to replace this in our proof with this, h of t. So this is going to be less than or equal to 2 times 2 to the h of t minus 1, like that. And then we can combine the 2 and the 2 because this is a 2 to the 1 and a 2 to the h of t. So just using properties of exponents, that's 2 to the h of t plus 1, then minus 1. And that was a lot of work, but I think that that is what we were trying to prove. Yeah, it is. I mean, these are written for T1 but and T2, but right, it was 2 to the height plus 1 minus 1. 2 to the height plus 1 minus 1. So that is what we were trying to get to. So that's the end of the recursive step or inductive step. So we just conclude. What was our conclusion? Do we remember what we were trying to prove? If T is a full binary tree, then the number of vertices in the full binary tree has to be less than or equal to 2 to the height of the tree plus 1 and minus 1. All right. So that was a proof. All right. So I think that's most of what we're going to do with the height of these trees right now. What I want to do is see if I can sneak in another proof before I have to stop. It's been 37 minutes. We can do one more. Yeah, so let me find something just from the homework for us to do. Yeah, okay, so let's just do one of these proofs here. Okay, so let's try, I'm using the 8th edition of the book, so it might not match up with the 7th edition of the book, but I'm going to do number 5.3.29. And I'm only going to do the proof part of it. So, so it's going to say let S be defined as, so here's the basis step. So the basis step is 0, 0 is in S. All right, so it's an ordered pair, 0, 0. And then the recursive part of the definition is going to say if AB is an S, so if A comma B is in S, then there must be some other stuff in S. What are they going to be? A, B plus 1 is an S. What else? A plus 1, B plus 1 is an S. And something else. A plus 2, B plus 2 is an S. Wait. 2 and 1. All right. So I think that's right. Yeah, and I guess we'll kind of do A. I don't really want to do all of these things. Yeah, I guess we're going to do A and B anyway, though. So let's see here. What's A? A is like, what are the first 4 applications of the recursive definition? I think they just want us to start writing out things in the set. All right. So what does the set contain? Well, it starts out with 0, 0, right? And then what you want to do is from 0, 0, we get new things using these three ways to get new things. So AB is 0, 0, right? That's the idea. So AB is 0, 0. So if AB is 0, 0, then AB plus 1 is going to be 0 and 1, right? So if that's A, that's B, then AB plus 1 is 0, 1. A plus 1, B plus 1 is going to be 1, 1. And then A plus 2, B plus 1 is going to be 2, 1. Okay, but then what you're going to have to do is each of these three things is also going to generate new stuff in the set. So I'm going to put comma, and then we're going to essentially just move these over here and do them again. So if you use that as your A and your B, then what stuff are you going to get in the set? Well, A, B plus 1 is going to be 0, 2, which we have not written yet, so we'll write it. A plus 1, B plus 1, so we're going to apply this, is going to be 1, 2, which, again, we don't already have, so that's worth writing. And then the last one is A plus 2, B plus 1, so that would be 2, 2. 2, 2. All right. Move that over and do it to the next one. So we're going to keep going here. So we got, that's our A and our B. So our next thing in the set is going to be A, B plus 1. That's 1, 2, which we've already got. So we can cross that out, but I won't yet. I lied, I will right now. We don't need that. A plus 1, B plus 1 is going to be 2, 3. Wait. A plus 1, B plus 1 is going to be 2, 2, which we already have. But, it was technically in there. And then A plus 2, B plus 1 is going to be 3, 2. So that's new, I think. All right. So that was our third application of the rules here. Taking the comma with me. It's fine. All right. Last one, 2, 1. Let's apply the rules. So A, B plus 1 is going to be 2, 2. Again, we do not need that. It's already written. A plus 1, B plus 1 is going to be 3, 2, which, again, we don't actually need that. It's already written. And A plus 2, B plus 1 is going to be 4, 2, like that. Okay. And, of course, it keeps going. All that stuff is in the set. So you just repeatedly apply those rules and you get more and more stuff. Hey, let's go now. More and more stuff that is in the set. So then what we want to do is we want to use strong induction to show that A is less than or equal to 2B. So now, part B, prove that if AB is an S, then A is less than 2B. Less than or equal to 2B. Okay, so that's what we're supposed to prove. So this should not be hopefully too hard. Let's try it. So this is a structural induction proof. So that means the way you do the basis step is you need to show the property for the smallest thing in the set. So we're going to show the property true for basically AB is what's the smallest AB? 0, 0, right? That's the basis of the set. So that's what we need to do. So, right, is 0 less than or equal to 2 times 0, question mark? Yes, that's true, right? Because that's just putting that in A and B for here and here. So that's true. Yes. Okay. Inductive step. So for the inductive step, you're going to assume that AB has the property, right? So in the recursive definition here, you've got this is in S, and then these are in S. So we are going to assume that this has the property, and then we need to show that all three of these also have the property, which I think we can do. So assume AB satisfies or is in S, and AB satisfies. I don't need to say satisfies. I can just say, and A is less than or equal to 2B. I can just write it. We need to show the property. I'm just going to say the property because it's going to be faster. For the new elements in the set. So we need to show that the property holds for, what were they? They were A, B plus 1. The other one was A plus 1, B plus 1. And then A plus 2, B plus 1. All right, so that's what we need to do. So you're just going to have to do those each separately. So so let's say we have A, B plus 1. So I'm just putting like this to indicate this is the one we're doing. So the property is A less than or equal to 2B. So A less than or equal to 2, and instead of B, it's B plus 1. And I don't know if it's true. So I'm putting that there. So A is less than or equal to 2B plus 2. And since I know that A is less than 2B, A is less than 2B, then that is true. I don't really like the way I did that though, but I'm just going to say true. All right, what's the next one? A plus 1, B plus 1. So is A plus 1 going to be less than or equal to 2B plus 1? And again, question mark, I don't know if that's true. So A plus 1 is less than or equal to 2B plus 2. I've got that. Let's just subtract 1 from each side. And I'll get A less than or equal to 2B plus 1. Question mark. Is that true? Again, that's going to be true, right? Because we know that, remember, that the A is less than the 2B already. So the plus 1 makes the right side bigger, right? And that's the same logic that I used up here. So that's also true. And then the last one, A plus 2, B plus 1. So A plus 2, B plus 1. So is A plus 2 less than or equal to 2B plus 1? Question mark. So we get A plus 2 less than or equal to 2B plus 2? Question mark. Subtract 2 from both sides, and you get A less than or equal to 2B, which is exactly the induction hypothesis. So this is also true. All right. So I just showed that if you have this, right, assume this, then all three of the new things in the set must also satisfy the same kind of property, and that's it. So we're done with that step. So now we can conclude or conclusion. What are we going to conclude? That if AB is an S, then A has to be less than or equal to 2B. The end. All right. So I think that's going to be it for right now. A little bit late for my office hours. So let us stop here, and I will talk to you guys later.